All right, here's our first example of how we use the conservation of energy concept to solve this problem. We have an object sitting on an inclined plane. It's given an initial speed of 20 meters per second. There's no friction between the surface and the block. And eventually, the block will come to a stop with a final velocity of 0. And the question is, how far up the incline will this block go if the incline has an angle of 30 degrees and the mass of the object is 10 kilograms? So the way to think about it is, if it goes up the incline along the hypotenuse, it will have gained a certain amount of height. So we can probably go ahead and solve for this first, and then go ahead and convert that to the distance along the incline. Because remember, on a triangle like that, there's a relationship between the hypotenuse, the opposite side, and the angle. We can say that the opposite side, or we could say the definition of the sine of theta is equal to the ratio of the opposite side divided by the hypotenuse, which means that the hypotenuse is equal to the opposite side divided by the sine of theta. When I exchange these two, and then of course, then if I plug in what these are, the hypotenuse is the distance traveled, the opposite side is h, and of course, that'd be the sine of theta. So once we find h, we'll find d by using this relationship right here. Now, let's go ahead and set up the equation we're always going to use. Any work put into the system plus any initial potential energy that it has plus any kinetic energy initial that it has must add up to the final potential energy plus the final kinetic energy plus any heat lost or energy lost due to friction or anything like that. So we always put down that equation. Now the next step is to figure out which ones of these we don't have. We don't have any work input. Now we kind of do, because we had to do something to get the object moving at 20 meters per second, but that's not part of the problem. We already take that into account by saying it has as much kinetic energy. Once we give that block a push, we don't keep pushing it up the incline, so we don't put any additional work into the system. So work put into the system is 0. They told us that there's no friction, so therefore there's not going to be any energy lost during the process. We're also told that when it gets to the very top here, the final velocity is 0, and if it has no velocity, that means it has no kinetic energy, so that goes to 0 as well. And here's one more trick. Even though the block appears to be starting at some initial height above the ground, we can just arbitrarily call that 0 height. And get rid of that, we can call this the increase in height. And so therefore, we can assume that it has no potential energy when it started. So we can arbitrarily put the 0 height at any place that we want to make it convenient for the problem. So therefore, in this case, we can say that we had no initial potential energy. And then this whole equation simply boils down to the initial kinetic energy is equal to the final potential energy. And of course, the initial kinetic energy is equal to 1/2 mv initial squared, and the final potential energy is mgh final. So what are we looking for now? We're looking for this increase in height. We're looking for h. That means we want to divide both sides by mg. Now first, I can go ahead and divide both sides by m. And then if I divide both sides by g, this comes over here. And I can write this as h final is equal to 1/2 the initial velocity squared divided by g. If I plug in the numbers, I get 1/2 times the initial velocity, which is 20 meters per second. And I can square that divided by g, which is 9.8 meters per second squared. And that will give us the final height. So that gives us 400 divided by 2 and divided by 9.8. And that gives us 20.41 meters per second. All right, that's how much height it gained, but that's not how far it traveled up the incline. For that, we need to plug that number in here. So the distance is equal to, it's not per second, it's height, it's just 20.41 meters. So 20.41 meters divided by the sine of 30 degrees. And of course, the sine of 30 degrees is 1/2, so it's like doubling that times 2, and roughly it goes a distance of 41 meters before coming to a stop. So notice how easy that problem becomes when you use that equation like that. Might as well use all the potential terms that could be in that equation. put in all the potential terms that could have a value in the problem, then get rid of the ones that do not, and whatever is left over, solve that for the unknown variable, which in this case was the final height, which then is used to find the distance traveled up the incline. And that's how you do a problem like that.